A flat expanse of fine gray gravel extends to a geometric line of heavy fencing, where a row of galvanized steel poles disappears into the low fog of a southern valley. Beyond the boundary, the ground drops toward a sluggish river channel that has moved less than 40 meters in 2 centuries. There are no signs warning of deep shafts, no vintage concrete structures visible above the scrub oak, and no steam venting into the morning air. Then the surface breaks. A series of deep drilled wells, lined with high-density polymer casing, sinks through 600 meters of dense shale to reach a pressurized brine basin that has sat completely isolated from the atmosphere since the Jurassic period. What is remarkable about this hidden brine reserve is not that its liquid holds thousands of metric tons of dissolved lithium, but that for over 80 years of intensive petroleum extraction directly above it, the water was pumped to the surface as industrial waste and re-injected straight back into the earth without a single chemist measuring its concentration. Where across the 13 provinces and territories of Canada do similar forgotten deep-seated fluids wait in ancient sedimentary basins, and what happens when the technological threshold to extract their strategic minerals is finally crossed. Before airborne sensors and modern geochemistry reframed the deep subsurface, early geological surveys treated the ancient salt formations of Western Canada as simple structural barriers or straightforward sources of industrial halite. The assumption that deep basin brines were uniform, exhausted byproducts of oilfield operations was entirely reasonable when petroleum engineering focused strictly on hydrocarbon volumes. The first crack in that long-held view appeared not through a sudden discovery at the surface, but through systematic sampling of forgotten water chemistry logs buried in provincial archive files. To understand how hundreds of millions of cubic meters of mineral-dense fluid came to sit sealed beneath Western Canada, one must look back 360 million years to the Devonian period. At that time, what is now the Western Canada Sedimentary Basin lay near the equator, covered by a shallow inland sea. Coral reefs flourished across northern and central Alberta, creating porous limestone formations such as the Leduc, and Swan Hills reef complexes. As the climate shifted and the sea evaporated under arid atmospheric conditions, vast beds of halite, anhydrite, and potash precipitated out of solution, capping the porous carbonate structures beneath thick, impermeable evaporite beds. For tens of millions of years, organic matter buried within these organic-rich shale formations transformed under high subterranean temperature and pressure into conventional oil and gas. Surrounding these hydrocarbon traps were ancient pore waters, trapped during the original deposition of the marine sediments. As geothermal heat warmed the deep rock layers, and chemical interactions between water, clay minerals, and limestone host rock proceeded over geological epochs, the salinity of these isolated fluids multiplied to levels more than 6 times that of modern ocean water. Lithium, leached slowly from surrounding volcanic ash beds and Precambrian silicate basement rocks, accumulated in these hyper-saline aquifers without any natural pathway of escape. When commercial drilling began in Alberta during the mid-20th century following the historic 1947 Leduc discovery, field operators were focused exclusively on light crude oil and natural gas reserves. Drilling rigs routinely penetrated the Devonian formations at depths ranging between 2,000 and 3,500 meters, bringing up continuous mixtures of oil, natural gas liquids, and heavy formation brine. Petroleum engineers viewed the water as a costly operational hazard. It corroded carbon steel casing, required complex separation equipment on the surface, and had to be continuously pumped back down injection wells into deep, isolated formations to maintain overall reservoir pressure. Throughout the peak decades of conventional production from 1950 to 1990, millions of routine water samples were collected across the Western Canada Sedimentary Basin. Technicians routinely logged basic physical parameters such as total dissolved solids, specific gravity, and primary chloride, sodium, and calcium concentrations. However, rare trace elements like lithium, rubidium, strontium, and cesium were almost never measured or recorded in routine oilfield water logs. The Geological Survey of Canada and the Alberta Geological Survey eventually compiled these historical water analyses into public digital databases, yet the economic potential of the dissolved battery metals remained hidden behind routine chemical shorthand. The critical trigger that transformed these forgotten fluid records from an operational nuisance into a strategic asset came with the rapid global transition toward battery storage and electric vehicles in the early 21st century. As conventional hard rock pegmatite mining in Western Australia and solar evaporation ponds in the South American Lithium Triangle face supply chain bottlenecks and severe water usage constraints, exploration geologists re-examined historical water chemistry data stored in Canadian provincial databases. They discovered that specific Devonian carbonate formations, particularly the Leduc reef trend stretching across central and west-central Alberta, contained consistent lithium concentrations exceeding 50 milligrams per liter, with specific reservoirs reaching over 100 milligrams per liter across hundreds of contiguous square kilometers. However, extracting dissolved lithium from billions of liters of deep subterranean brine presented an unprecedented chemical and engineering hurdle. Traditional evaporative solar ponds, which require vast land areas, continuous sunlight, and years of settling time in arid environments, could not function in the cold, forested climate of northern Alberta. How could industrial engineers extract thousands of metric tons of invisible lithium from a continuous, high-volume flow of hot, corrosive brine without destroying the delicate subsurface equilibrium of the sedimentary basin? The verification of deep-seated lithium reserves across Western Canada did not come from a single dramatic drilling strike, but from a fundamental change in analytical laboratory methods. For half a century, standard oilfield water testing relied on basic titration and gravimetric analysis, laboratory methods designed primarily to calculate total dissolved salts rather than trace metal components. When inductively coupled plasma mass spectrometry, an advanced instrument capable of measuring chemical concentrations down to parts per billion, became widespread in geochemical laboratories during the 1990s, geologists began reanalyzing archival brine samples through the new digital hardware. Researchers at the Alberta Geological Survey and the University of Alberta re-examined thousands of preserved drill stem test fluids stored in government core repositories. By cross-referencing three-dimensional seismic reflection surveys with deep wireline well logs, hydrogeologists mapped the precise spatial distribution of lithium-rich fluids within the Devonian, Leduc and Swan Hills formations. The seismic data revealed that the highest metal concentrations did not sit randomly throughout the basin. They aligned systematically with ancient reef margins and structural fault zones where high-temperature hydrothermal fluids had migrated upward from deeper Precambrian basement rocks. To confirm that the metal concentrations were stable and recoverable on an industrial scale, field engineering teams conducted long-term pumping tests on suspended oil wells. Geochemists applied stable isotope analysis, measuring the ratio of lithium-6 to lithium-7 to trace the precise geological origin of the subterranean fluid and verify that the aquifer was not diluting with shallow groundwater over extended production runs. The physical results confirmed that the deep formations contained homogeneous, highly pressurized brine reservoirs stretching across hundreds of contiguous square kilometers of the Western Canada sedimentary basin. The shift in perspective was complete. Wells drilled 70 years prior to extract petroleum were re-evaluated using modern direct lithium extraction technologies, which utilize selective sorbents and engineered ion exchange resin beads to strip lithium ions directly from raw brine in minutes, returning the stripped fluid to the target formation via injection wells. What had been logged for decades as unproductive wastewater was recognized as one of the largest continuous lithium accumulations on the North American continent. Yet, transforming verified subsurface geochemistry into a functioning industrial operation requires moving billions of liters of subterranean fluid to the surface without disrupting regional hydrology. What happens when this massive subsurface infrastructure meets the physical reality of northern industrial development, land management, and environmental oversight. Today, the economic and infrastructure implications of lithium extraction from oilfield brines across Western Canada are taking concrete physical form. Commercial operations in south-central and west-central Alberta are being constructed directly upon existing industrial footprints. Well pads, gravel access roads, pipeline rights-of-way, and electrical grid connections, originally built for conventional petroleum extraction, are being adapted to pump, process, and re-inject formation water, avoiding the extensive land clearing typically associated with conventional hard rock mining operations. The true scale of the underlying resource is confirmed by technical reports filed under National Instrument 43-101 regulatory standards. Within the Leduc Formation near Fox Creek, independent hydrogeological evaluations have outlined measured and indicated resources exceeding 1 million metric tons of lithium carbonate equivalent. Rather than digging open pit mines or clearing square kilometers of forested land for evaporation ponds, direct lithium extraction facilities process brine in closed-loop modular plants occupying less than 2 hectares each. The operational reality, however, involves managing continuous, massive fluid movement. To produce 20,000 metric tons of battery-grade lithium hydroxide per year, a commercial operator must extract, treat, and re-inject approximately 60 million cubic meters of formation brine annually. This sheer volume requires precise subterranean pressure monitoring by the Alberta Energy Regulator to ensure that continuous, high-volume re-injection into deep rock formations does not induce localized microseismic activity or alter regional hydrodynamics. Surface water protection remains a critical regulatory parameter. Because the deep formation water carries high concentrations of sodium chloride, calcium, hydrogen sulfide, and heavy trace metals alongside lithium, spill containment protocols and pipeline integrity standards match those of major oil pipelines. Environmental monitoring networks operated by Environment and Climate Change Canada and provincial bodies continuously track groundwater chemistry around injection sites to verify complete physical isolation from shallow freshwater aquifers. For local communities and First Nations within whose traditional territories these projects operate, the transition represents a distinct shift in how industrial land is used. Commercial agreements now focus on long-term resource co-management, monitoring water quality, and leveraging existing technical workforces trained during the peak decades of conventional oil production. The surface infrastructure remains visually quiet, a series of modest pump houses, manifold sheds, and insulated processing modules set back quietly in the boreal forest. Yet as commercial production ramps up, a fundamental geographic question remains unanswered. How does a region defined for over 70 years by fossil fuel extraction redefine its relationship to the ground beneath it, when the primary asset is no longer what burns, but the invisible minerals dissolved in ancient, motionless water? As full-scale commercial testing continues across Alberta and Saskatchewan, the investigation into deep basin brines leaves one central question open. Hydrogeologists are still establishing how fluid pressure across deep fault systems will respond when millions of cubic meters of brine are continuously cycled out of one reef formation and re-injected into another over decades of continuous processing. What kept this immense resource completely invisible for 3/4 of a century was not a lack of physical samples or missing geological charts, but the single economic category under which the water was filed. It was recorded purely as waste product, and no one measures the economic value of what has already been defined as refuse. Significant geological uncertainties remain. The exact migration paths of thermal fluids from the underlying Precambrian basement into the Devonian formations are still being modeled by researchers at the Geological Survey of Canada. Furthermore, as older oil wells across the prairies are plugged and abandoned, the physical windows of access to these deep reservoirs are closing, leaving engineers in a race to map and secure infrastructure before wellbores are permanently sealed with concrete. The surface map presents a familiar picture of dirt roads, clear-cut lines and quiet pump jacks stretching to the horizon. Yet 3,000 meters beneath that landscape, the fundamental chemistry of the sedimentary basin is being reevaluated for a completely different technological era. Which forgotten landscape or unexpected industrial transition in your own province or territory has always made you look twice at the official maps? Share your observations in the comments below, and subscribe for more deep geological investigations across the country.